Okay, let's talk a little bit more about uniform convergence. And the first thing I want to do is the Weierstrass M-test. And this tells us when a sum or a series of functions converges. And it's only a one-way test. If something happens, then the sum converges, but it's fairly useful, especially with some power series. So suppose I'll name it Weierstrass M-test. Suppose f sub n is a sequence of functions defined on a set E, and suppose that f sub n of x in absolute value is less than or equal to m sub n for all x in E. Okay, so I've got a bound, a capital M sub n, a bound for f on its entire domain for each of the n's. Okay, then if the sum of the m sub n's from n equals 0 or 1 or wherever you're starting your sequence converges, then the sum of the f sub n's from n equals 0 to infinity, or wherever we started, it converges uniformly. Okay, so this is a good test to use if I have a series of functions that I'm trying to add up, and I can bound each of the individual things in the series, each of the individual functions in the series. So do note this is only a one-way test. If it converges uniformly, you might not be able to find some bound on each of the functions. But if you can find a bound on each of the functions, and the bounds have a finite sum altogether, then you have uniform convergence. So let's prove this. Okay, so if the sum of the m sub n's converges, then there is n in the natural numbers such that, well, we get Cauchy's criterion. The sum from n equals k to m of m sub n is less than epsilon. Then if it converges, then given epsilon, there is some n such that this is true for k and m greater than n. Okay, so that's just by our assumption. We have to show that the sum of the functions converges. So let's say the sum from I equals n to m of f sub I of x in absolute value. Well, I'm going to use the Cauchy criterion on the sum, and so this is the partial sum at x at m minus the partial sum at n minus 1 at x in absolute value. So these are the partial sums, and that's how we show the Cauchy criterion for a series. Remember, you look at their partial sums. So if I can bound this by epsilon, I'd get convergence of I'd have the Cauchy criterion on the partial sums, So the partial sums converge, the series converges. So this is less than or equal to the sum from n to m of the absolute value of f sub I at x, which is less than or equal to the sum from n to m of m sub n, which is less than epsilon by assumption. So the Cauchy criterion on the partial sums holds. S from I equals 0 to n f sub I at x giving uniform convergence of the partial sums, which is what we wanted to show. Okay, so that's the Weierstrass M-test, and it's pretty useful when we're dealing with series. Okay. The next thing I want to do is how uniform convergence and continuity work together. And so the theorem that we're going to use is going to say that the limits don't really matter which order you take them in, right? And what I mean by that is, if you're trying to prove continuity, you say that as you approach an input point, the limits of the outputs get close to the input, the output of that limit, right? So the limit of the inputs approaches the limit of the outputs at a sequence of inputs approaches the limit, the output at the limit of the sequence of inputs. So just recall, I'll write this down, that a function is continuous at, say, x in e bar if there is a, well, if any sequence s sub n going to x in e satisfies the limit as n goes to infinity of f of s sub n equals f of x. Right. So I'm trying to show this with a function, so I'm going to put some i's down here, and we're going to have to take another limit then. So this is f at the limit of the s sub n's as n goes to infinity. If I put i's here, well, I have two different limits now. I've got the limit as n goes to infinity, and I've got the limit as I goes to infinity of f sub I of s sub n. So I've got sort of that order of them. And then if I have continuity on this side, what I have is I've got this limit as I goes to infinity of f sub I at the limit as n goes to infinity of s sub n. So I can kind of rewrite that as the limit as I goes to infinity, the limit as n goes to infinity of f sub I s sub n. So which do I take first? Do I take the n's going to infinity first, or do I take the i's going to infinity first? And we're going to see with uniform continuity on functions, it doesn't matter which you take first. And so if you have a sequence of continuous functions that converges uniformly, their limit will also be continuous. Okay, so the theorem. Suppose f sub n goes to f uniformly, on E, and let x be a limit point of E, so it'd be an E closure, and suppose the limit as t goes to x of f of t equals a sub n f sub n for each n. So we do this for each n, and we get a limit as t approaches x for each n. So n is fixed in this statement. Then the conclusion is, then the limit of f sub t as t goes to x is equal to the limit of a sub n as n goes to infinity. So I've got my inputs approaching x, and I've got my functions getting closer and closer to f. So I've got that sort of which one comes first thing. And so if I rewrite this as sort of double function notation, or double limit notation, I've got the limit as t goes to x here of the limit of f sub I at t as I goes to infinity. So I goes to infinity first. I go out with each of the functions. That's equal to, well, the limit of n going to infinity, and then the a sub n's is the limit of the x's going to t at f sub n of the t's going to x of f sub n at t. Okay, so this is what we're going to try and prove here. So let's let epsilon be bigger than 0. Okay, this by uniform convergence, there's is a n such that for n and m bigger than n and t and e, so by uniform convergence I get all the t and e, and by convergence I get some capital N where I'm going to use Cauchy, that f sub n at t minus f sub m at t is less than epsilon. Okay, so letting t approach x, then we get that the absolute value of a sub n minus a sub m in absolute value is less than or equal to epsilon for any m and n bigger than n. Okay, so I'm taking limits, and the limit of something smaller than epsilon could be equal to epsilon or smaller than epsilon. Okay. And this means a sub n is Cauchy as a sequence, so has a limit. Say the limit as n goes to infinity of a sub n is equal to, by definition, a. So what I have to do now is I have to show that a is the limit of the a sub n's, And what the theorem says is the limit of the a sub n's is approaching the limit of f. So we need to show that f sub t minus a is less than epsilon for t close to x. Alright, so let's look at f sub t minus a. F of t minus a. Well, we're going to use the triangle inequality and we're going to add and subtract a bunch of things. So I've got f of t, and I'm going to add and subtract f sub n at t, and use the triangle inequality on those. So I've added and subtracted, and then I've used the triangle inequality, and I'm going to add and subtract a sub n as well. So, and then minus a. So add and subtract a sub n, add and subtract f sub n at t, and use the triangle inequality twice, and you get this less than or equal to with the sum of those three absolute values. Okay, so if I can make all three of these things small, we're going to be good. If each of these three things is small, their sum is small, so f of t minus a has to be small. So we can first choose this guy small for some n f sub t minus f sub n at t is less than epsilon over 3. I'm going to call that n1. Whenever n is bigger than n1, and this is by uniform convergence of the f sub n's. Okay. We can also choose some other n2 for some n2, the absolute value of a sub n minus a is less than epsilon over 3 by convergence of a sub n to a. That's just sequence real number convergence. And because f sub n at t converges to a sub n, remember as t goes to x, we can find some neighborhood of x such that if t is in this neighborhood of x, then the absolute value of f sub n at t minus a sub n is less than epsilon over 3. Okay, then if we put these things together, then for n bigger than n1, just say plus n2, that makes it plenty big enough, and t in n of x intersect e, we have what we needed, which was f of t minus a in absolute value is less than epsilon over 3 plus epsilon over 3 plus epsilon over 3 equal to epsilon. And that proves that. Okay, the immediate corollary is if f sub n goes to f uniformly and f sub n is continuous for each n, then f is continuous. And maybe I should say on E and on E if that's not obvious. Okay, so that's how uniform convergence and continuity play well together. In the next video we'll talk about how uniform convergence and integration play really nicely, and then we'll look at integration or differentiation and uniform convergence, and they don't work quite as well together, but we can say some things about them. So we'll state a theorem about differentiation and uniform convergence.